In this video, we're going to talk about the derivatives of the hyperbolic functions. Now, some students, they don't experience these derivatives this early on in the calculus series. It's quite a bit later, but some of the students have told me that they need to see derivatives early. So this video is just going to talk about the very basic skimming, just a little bit over what a hyperbolic function is, and then how to take the derivative of it. The different things like domains, proofs, manipulations, different other strategies that you would use with them, that's going to be quite a bit farther down the road, because we're going to finish up derivatives, then we're going to do everything you didn't know you wanted to know about graphing using calculus strategies, and then we're going to talk about the transcendental functions, and at that point I'll get into more of the details. And so I hope this helps those of you that need to have this early on, and if you don't, just skip this part. All right, now let's talk about hyperbolics for just a second. Now, when you did the trig functions, right, and you learned about them, and they would have you plot them off and graph them with, I'm going to do my best to draw a circle with the unit circle. All right, so then what you had is a point that was based on cosine and sine as you went around, right? And this was based on x squared plus y squared equals 1, right? The Pythagorean theorem, sine squared theta plus cosine squared theta is equal to 1. Now, for us, what we're going to do is all of these, kind of the same thing, you can trace them through, but instead of them being traced through on a circle, they are being traced through on a hyperbola, to where the point would travel along the hyperbola. Let's call it P, and it would be the hyperbolic cosine and the hyperbolic sine. All right, and it is based on x squared minus y squared equals 1. I could write that just a little bit better. X squared minus y squared equals 1. So do you see already there's some similarities in the formula and how we're going to plot this through? So the hyperbolic sine, these are based on this, and my negatives, I'm sorry, the software that I use doesn't show up very well. E to the x minus e to the minus x over 2 is hyperbolic sine, and e to the x plus e to the minus x over 2 is a hyperbolic cosine. And remember, they get their names from the fact that they're tracing a hyperbola, all right? But once you get that set up, there are some similarities and some differences with the trig functions that you know. You know, before you knew that tangent of some angle is equal to sine over cosine. Well, hyperbolic tangent right here is equal to the hyperbolic sine over hyperbolic cosine. You knew that that cotangent was cosine over sine, so hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, right? And you know that cosecant was 1 over sine x, and hyperbolic cosecant is 1 over hyperbolic sine x. It's kind of a mouthful. All right, and secant, hyperbolic secant of x is 1 over hyperbolic cosine of x. You just have to laugh. All right, now, so that's kind of where the similarities sort of follow a pattern. I wanted to show these to you side by side. Again, we can see a gap in this little shadow. This is a minus sign. I'm not sure why it doesn't show up more. I'm going to color these in. All right. Now, when you learn the derivatives of the trig functions, I had told you that everything that started with a C had a negative in front of it, right? But if you'll notice here, here's the derivative of hyperbolic cosine, and it does not have a negative in front of its derivative. But you can kind of see some patterns, right? The derivative of cosine is negative sine x, but the derivative of hyperbolic cosine is positive hyperbolic sine. So there's some similarities and some not. So just sort of look back and forth between these two lines and take a minute to see what's the same kind of pattern and what's not. Okay, and especially pay attention to what's not the same. Because before, for instance, this regular secant didn't have a negative, but hyperbolic secant has a negative over here. So just take a second. Okay, now I don't know if your teacher is going to provide these for you or if they're going to make you memorize them. They're not used that frequently in my experience at this level. So we use them later on for other things. But I just want you to kind of look this over, and hopefully you know by now whether your teacher is going to make you memorize this or whether they're going to provide you a formula sheet. Now, the other thing that you might want to kind of be aware of, this actually helps more in limits, right? But when you had the graphs, you know what the sine curve looks like, right? But the hyperbolic sine curve looks almost like the tangent curve. Okay, so this is the hyperbolic sine curve. And the hyperbolic cosine curve looks kind of like this. This is one. Okay, and then the hyperbolic tangent curve looks like this. Just so that you can see that they didn't, it does have a pattern, I guess. All right. Not that that's going to help you with derivatives, right? Now, there are some other similarities. For instance, in trig, the regular trig, you would have sine theta squared plus cosine squared theta is equal to 1, right? And now we have hyperbolic cosine squared theta minus hyperbolic sine squared theta is equal to 1. And there are other things, but like I said, that's going to be for later. So for right now, let's just do some derivatives. So what if we have y is equal to x hyperbolic sine of x minus the hyperbolic cosine of x? All right. Now, so if you look up here, the derivative of the hyperbolic sine is hyperbolic cosine, and the derivative of the hyperbolic cosine is hyperbolic sine. And this first term is a product. So what you're going to have is the first times the derivative of the second, and the derivative of hyperbolic sine is hyperbolic cosine. Sooner or later, I'm going to get tongue-tied. I'm already starting there. Okay, plus the second times the derivative of the first minus, and the derivative of the hyperbolic cosine is hyperbolic sine. All right, now, if you look, this hyperbolic sine of x times 1 is the hyperbolic sine of x minus the hyperbolic sine of x again, just leaves you this x times the hyperbolic cosine of x. Not too bad. All right. So what if we had y is equal to the natural log of the hyperbolic cosine of x? And some people will go back and pick up that e to the x plus e to the minus x over 2, but that, unless your teacher asks you to do that, that would not be the intent. So let's take the derivative the way it is. So remember, the derivative of the natural log is 1 over u du, right? So this is 1 over the hyperbolic cosine of x times the derivative of the hyperbolic cosine, which is the hyperbolic sine of x. And the hyperbolic sine of x over the hyperbolic cosine of x is the hyperbolic tangent of x. All right. Yeah. I don't know why I laugh so much through here. I think I just laugh at myself because I'm just waiting, to get just completely lost in here somewhere with trying to say all these hyperbolics. All right. So what if you have the hyperbolic cosine of x times the hyperbolic sine of x? And you remember way back when we were talking about limits and derivatives and things, and I had said you always need to take like 30 seconds and see if there's something you can, well, not 30 seconds, 5 seconds to see if there's something that you can do to reduce this. Now remember, hyperbolic tangent is hyperbolic sine of x over the hyperbolic cosine of x. So if these are multiplied like this, and I have not taken the derivative yet, then this hyperbolic cosine cancels this hyperbolic cosine, and you have the hyperbolic sine of x, right? Now, if you write that down and box it in, I think your teacher's just going to smile because they know what happened. You got so busy cleaning this up, you didn't notice you didn't take the derivative. And so, but you haven't taken the derivative yet. So the derivative of hyperbolic sine is hyperbolic cosine. All right, let's do one that's a little worse for wear. So here's y is equal to the hyperbolic cotangent of x. I have to think about that. Over 1 plus the hyperbolic tangent of x. Okay, that's my goal. All right, so this would be the quotient rule. So it's the bottom times the derivative of the top. And the derivative of the hyperbolic cotangent is negative hyperbolic cosecant squared of x. Notice that the square right here comes after the h, right? It's not cosecant squared hyperbolic. It's hyperbolic cosecant squared. So be careful where the square is. Minus the top times the derivative of the bottom. And the derivative of 1 is 0. And the derivative of the hyperbolic tangent is the hyperbolic secant squared of x. All over the bottom don't forget my x squared. Okay, there we go. We're hanging in there. Now, let us look and see if there's anything that we can do. I can pull this negative out in the front. It looks like maybe some of this stuff might maybe reduce somehow, so I'm going to change it into sines and cosines, all of them being hyperbolic. So I would have the minus, and this would be 1 plus the hyperbolic sine of x over the hyperbolic cosine of x. Okay. Times 1 over the hyperbolic sine squared of x. Okay. Minus the hyperbolic cosine of x. You try saying this a few times. Over the hyperbolic sine of x times 1 over secant is 1 over cosine, right? So this is 1 over the hyperbolic cosine squared of x. There. All over. And for right now, I'm just going to leave the bottom the way it is until I see if the top does anything interesting. 1 plus the hyperbolic tangent of x squared. Okay? Now, when I multiply this out, you can kind of see that nothing over here is going to cancel. But when you multiply this here, one of the hyperbolic signs cancels the other one, right? And likewise here, when you multiply this over, one of the hyperbolic cosines is going to cancel the other one. So what happens is you get, when I multiply it, I have minus 1 over hyperbolic sine squared of x times 1 is just that self, so I'm going to change it back to cosecant. So hyperbolic cosecant squared. All right, now I'm going to distribute the minus while I go. So, and then this sign is going to cancel one of those hyperbolic signs. And so I've got 1 over the hyperbolic cosine times 1 over the hyperbolic sine. So this is going to be minus this hyperbolic secant of x and the hyperbolic cosecant of x. All right, minus, right, and this hyperbolic cosine cancels one of these. So I have 1 over the hyperbolic sine times 1 over the hyperbolic cosine. So it's going to be minus cosecant, the hyperbolic of x, hyperbolic secant of x, all over 1 plus the hyperbolic tangent of x squared. Okay. All right. So let's see. These two are the same, just switched around. So I have 2 of those. Let's put the cosecant in the front, hyperbolic cosecant. All right. All right, we can do this. We're tough. Right? And do you see that there's a negative hyperbolic cosecant of x in common? All right. So we're going to factor out a negative hyperbolic cosecant of x from, and that's going to leave me an hyperbolic cosecant of x plus 2, because remember, I'm factoring out a negative. Hyperbolic secant of x over 1 plus, that looks like a plus the tangent. Tangent hyperbolic x quantity squared. And that's as good as I'm going to get. Okay, so this is the answer. We should make math tongue twisters. You know how they always go, how does that go? Peter Piper picked a peck of pickled peppers or something. All right, we should do that with math. Now, here we go. Let's try a new one. Here's the hyperbolic secant squared of 3x plus 5. Now, there are inverse hyperbolic functions, just like we had inverse trig functions. And I'm going to have a very brief little video that tells you how that works, and then we're going to investigate it also in detail later on. But for right now, let's just kind of do this. And remember how we originally said, until you got used to it, that it might be better with these shortcut powers that they squeeze in right here to put it out here where you can see it. It's not a -1 or anything, it's just a 2. So this is the power rule. You bring the 2 down, you leave the inside alone, You take 1 off the power, you loop back in and take the derivative of the inside. And this is, I don't know, I'm going to give it a try to say it. So you remember how the derivative in old trig, the derivative of secant was secant tan, right? So the derivative of hyperbolic secant is hyperbolic secant hyperbolic tan, and this one has a negative because it's not the same as trig. So this is negative, and we would have the hyperbolic secant of whatever's in there and the hyperbolic tangent of whatever's in there. Then you loop back in and take the derivative of whatever's in there, and that's what this is. Okay? Now what can we do? We can pull the 3 and the negative and the 2 out, and so that, well, I could also change this to y prime. We would have -6. We would have 2 of these hyperbolic secants, so we'd have hyperbolic secant squared of 3x plus 5 back again. And we've acquired a hyperbolic tangent of 3x plus 5. Now this is pretty basic. I'm just going to leave this there with you in good hands, and we'll come back to this in detail at a later time. So I hope this helps those of you that have to do derivatives right at this moment for your particular book and your particular requirements for your course. So there will be some practice problems and there will be some links, and we will address this in greater detail later. Don't forget to like and subscribe. And if you have a comment, please leave one. All right. And I will talk to you in the next video.